Hi, my name is Ron Lynch. I do web handling training and consulting, and this presentation is on rollers and traction. First, we're going to talk about roller functions and types, then some design considerations, the capstan formula, and air entrainment. Rollers divide into a couple of basic types. There's driven rollers and there's idlers. Generally, driven rollers are used to control the velocity of the web, and they break down into two types. General transport rollers, which might be NIPs, SRAPs, single-driven rollers, used basically just for transportation, and then process rollers, whose objective is to alter the properties of the web. These might be lamination rollers, calendar rollers, embossing rollers, or heating and cooling rollers. Idlers are simply to change the direction of the web or to control its position. Either turn the web up or down to prevent sag in otherwise long spans, or to act as a backup to a process. When I think about design considerations, there could be a whole section on this alone. Process needs, roller design, mounting design, and economics. Under process needs is the role for heating or cooling the web. What surface temperature do you need? What length of contact does the web need to be against the roller? What pressure profile does the roller exert against the web? Does it need to have a special covering? What about surface roughness? What about pattern and coating? And so a lot of process needs. Roller design itself, you've got to think about speed, balance, critical speed to avoid vibration, what width or how much wider than the web does the roll need to be for run out, what loading effects will there be, what deflection can you tolerate, which can lead to questions about diameters and diameter tolerances. What environment does the roller run in? What material is the web and the roller need to be? Do you have to consider static electricity? If it's an idler, you've got to think about idler drag, inertia, and in all cases, traction with the roller. Mounting design. Is it a live or dead shaft idler or driven roll? Is it cantilevered or simply supported? There are alignment tolerances that you have to consider, and stiffness of the mounting. You can have a very well-designed roller on a very flimsy frame and it still moves around in inappropriate ways. And economics, of course, the quantity that you're going to make, the cost, the life cycle that you're looking for, and the maintenance cost along the way. Now we're going to move into friction and traction. A couple of definitions that may seem obvious, but first is in traction. What does traction mean? Well, it means not sliding. There's no relative motion between the web and the roller surface. And then sliding there is relative motion between the two. It's not in traction. So if the roller is going at one speed, the web may be going at a different speed. The frictional force is the force that is generated between a web and a roller surface that prevents motion. Some force is needed to cause one surface to slide over another, and frictional force resists that motion. Normal force is the force that is pressing two surfaces together, of course, normal to the plane of contact. And the coefficient of friction is the ratio of the frictional force that's developed to the normal force at the onset of sliding. Now we have static coefficient at the onset of sliding, and we have a kinetic coefficient of friction during sliding. Why are friction and traction important? On rollers, tension control is based on velocity control. Traction is required to transmit a driven roller's velocity to the web. Tracking is based on steering control, which requires traction between the web and roller. This is true for both driven rolls and idlers. The webs follow the right angle rule, which says if you're in traction, the web approaches a roller at right angles to the axis of the roller. This is true for webs. This is true for your tires on the road. Dust and damage can result from unintended sliding of a web on a roller surface. You can pick out fibers, scratch the web, create all kinds of problems. Now, on sliding surfaces like bow bars, turn bars, guide bars, things like that, consistent tension ratios are important, and they're based on coefficient of friction and the tension ratio across the sliding item. With rollers or with sliding surfaces, understanding coefficient of friction and traction is always important. Now, if we look at the coefficient of friction, we go back to what we learned in school where we're pushing rigid blocks on flat surfaces. And so we've got a normal force, which in this case, in the picture on the left, is the weight of the block pressing it against the surface. You have a pulling force P trying to slide the box, and a frictional force that develops to resist motion. Now, if we look at the graph on the right, if we pull with a small pulling force, a small frictional force will develop to resist that, and nothing will happen. If we pull a little bit harder with a pulling force, more frictional force is developed. Eventually, if we pull hard enough with a pulling force, friction will reach a maximum value and the block will start to slide. That happens when the maximum frictional force is equal to mu times the normal force, coefficient of friction times normal force. Now, if we pull harder, it will slide and accelerate. In fact, the coefficient of friction will drop a little bit once it starts sliding. What comes out of this is the formula where coefficient of friction, mu, is constant and it's proportional to the pulling force divided by the normal force. If we look at flexible webs on curved surfaces, things change a little bit. If we think about a web, we've got two tensions on it on either side of the non-rotating surface. And if those tensions are equal, nothing happens. If we pull a little bit harder on one side, a frictional force will develop to resist motion and it won't slide. Harder still, it won't slide. A little bit harder still, it won't slide. Eventually, we pull hard enough that the web will start to slide in the direction of the high tension. Without going through all of the mathematics that apply here, what comes out of this is what's known as the Capstan formula. Tension high divided by tension low is equal to e to the mu theta. Mu, again, is our coefficient of friction. Theta is the wrap angle of the web on the surface in radians. And TH over TL, commonly the tension ratio. It's called the Capstan formula, but it does go by a lot of other names. Just to be sure, when we're talking about idlers, the tension difference to cross an idler, TH and TL, is due to the drag of the idler. When we look at a driven roll, the tension difference across the driven roller, TH over TL, is due to the speeds of the driven rollers. What we're using the Capstan formula for with driven rollers is to make sure that we can develop enough friction to keep the web from sliding on the surface that it's in contact with, so that its TH over TL has to be less than the e to the mu theta value. For rollers, the Capstan formula does not calculate the tensions. It's used as a slip check. COF is a property of two surfaces, the web and the surface that it contacts, and it can vary over time. Because of the two surface thing, your roll supplier, if they don't know what web you're going to use, they can't tell you what the COF is going to be. Your web supplier, if they don't know what rolls you're going to run it on, can't tell you what the coefficient of friction is going to be. The only place where it can actually be calculated and known for sure is when you bring the two together in your plant. Typically, it is up to the user to calculate and understand coefficient of friction. And it can vary over time. Clean rolls versus dirty rolls, new rolls versus old rolls, environmental conditions, they can all affect the coefficient of friction. And so it is not a perfectly constant value. And it's one of the reasons we tend to be fairly conservative when we think about coefficient of friction. Generally, high coefficient of friction is good for traction on rollers, for tracking, and for tension control. Low coefficient of friction is good if you have sliding contact, but interesting enough, it's also good for avoiding wrinkles. And so if you have low coefficient of friction on a roller, the web might be able to squirm around a little bit on the surface of a roller and flatten out and avoid wrinkles. Coefficient of friction can be measured a couple of different ways. There's typically a hand test that's fairly common, and there are a lot of coefficient of friction testers that you can purchase. The hand tests are fast and easy to do, low-cost equipment typically, easy to customize. You can do them in a machine, you can do them offline, but they are hard to formalize, so they typically aren't seen in specifications and things like that. With coefficient of friction testers, it's very easy to formalize a test, but they're typically limited to flat samples of material. It is equipment you have to buy, and it can be expensive. But if it's locked away in a lab, it may be hard to have access to or schedule time on. This shows a typical by hand test where we have a non-rotating surface, a web wrapped around it, and if you allow gravity to do its job, you get 180 degrees of wrap or pi radians of wrap. We have a low tension hanging on one side of the web, TL, just a weight, any weight, that puts the web at approximately the same stress levels you see online. And then on the other side of the web, we have a force gauge, TH. And so as you pull on the force gauge and slowly slide the web over the surface, you're measuring TH against the hanging weight, TL. Now, we can plug this into the Capstan formula that we've solved for coefficient of friction. We find the tension ratio, which we've just measured. We can take the natural log of that. We can divide it by the wrap angle, theta in radians, pi in this case. And in an example here, if TH is 1 pound and TL is 0.5 pounds, our coefficient of friction calculates out to be 0.22. Coefficient of friction test equipment, a couple of examples here. One is a motorized sled that is pulling a sample of the material under a known weight and measuring the force that's applied to the weight. Or you can have an angle tester where you increase the angle until the sample slides down the surface and the tangent of that angle is equal to the coefficient of friction. As I said earlier, the Capstan formula is used to do a slip check. On driven rollers, which would include friction drive rollers like S-wrap, single driven rollers, etc., you're controlling the velocity of the web, and this is only if they're in traction. For driven rollers, either the upstream or the downstream span can be the high tension. So the Capstan formula doesn't say upstream over downstream, it's simply high tension over low tension. Now, normally nips are assumed not to slip under most conditions, but I have seen nips slip if they're not properly loaded and if they're badly worn. But the Capstan formula does not apply to a normal nip situation. For idlers are driven by friction with the web, so there must be sufficient traction to actually drive the idler at the speed without slipping. In steady state, the downstream tension is the higher tension, and we use the Capstan formula to do a web-to-roller slip check. Some examples of this in this slide, if we look at the S-wrap, now just an example here, we have two driven rollers traveling the same speed with the same coefficient of friction. To get the wrap angle, you can add the wrap angles of the two individual rollers. So here we've got 180 degrees plus 180 degrees, 360 degrees of wrap, so theta is equal to 2 pi radians. If we look at a single driven roller, of course you can use an idler to enhance the wrap on this past 180 degrees. And so in an example here, we're going to do a slip check on a single driven roller. It's got a 200 degrees of wrap. It's got a coefficient of friction of 0.5. We plug this into the e to the mu theta calculation, and we get an e to the mu theta value of 5.72. So if we look at the tensions, if one tension is 150 newtons and the other one is 35 newtons, that gives us a 4.29 tension ratio, which is less than our 5.72 e to the mu theta value. So that would not slip. But it is fairly close. If we were to think of our low tension going down to 25 newtons, well, that gives us a 6-to-1 tension ratio, and that would slip. So a tension difference of only a few newtons, especially on the low tension side, can make a big difference between slipping and not slipping. So we normally apply a safety factor. In this case, there is no definite way of doing it. I simply divide the e to the mu theta value by 2. And if I'm designing driven rollers, I like to keep my TH over TL less than that number. An example of how we use that, this is a web path that we've done some calculation on. If we look at our first SRAP here, which is our master roller, we definitely don't want to slip there. If we look at T3, it's 100 newtons. If we look at T4, it was calculated out to be 69 newtons. Our TH over TL is 100 over 69, or 1.45. Our e to the mu theta value for the wrap angle and coefficient of friction that we're given is 4.11. So our tension ratio is much less than our e to the mu theta value, so this will not slip. In fact, we've got a very generous safety factor here for this one. If we look at our second driven roller here, our SRAP between spans 8 and spans 9, we've got 200 newtons on one side, 30 newtons on the other. Our e to the mu theta value for this is still 4.11. Our actual tension ratio is 6.67. This roller will slip, and we'll talk about that in a minute. Now, you can also apply this to an idler. If we look at this idler now, our tension ratio, TH over TL, is 35 newtons over 30 newtons for a tension ratio of 1.17. Our e to the mu theta value is 1.6, so this will not slip. Now, I'm usually not as conservative with the safety factors for idlers. Maybe they'll slip a little bit on startup or a little bit on shutdown. If it's not a fatal situation that causes a breakout, you can be a little more relaxed with the safety factors. Now, if we go back to our slipping SRAP and we look at the capstan formula, there's 4 variables in that formula: TH, TL, coefficient of friction, and wrap angle. We're at liberty to change any one of these 4 variables, at least during initial design, and you get to choose how to fix this problem. So you could increase the coefficient of friction by buying a more exotic coating for the roller. You could increase the wrap angle by changing the orientation of the rolls. With an SRAP, you can easily get about 360 degrees, or if you even nest them a little bit, you might get up to 540 degrees. You can lower T8 or you can increase T9. And so how you solve it depends on your situation. Now, my first thought here is also most webs would have a hard time doing a 6.7 to 1 tension drop over a driven roller. That's a potential wrinkle problem. It's a potential viscoelastic recovery problem. And so I would try and lower the tension ratio before I would start thinking about coefficient of friction and wrap angle. And I would also ask myself, why do I have 200 newtons in T8 if I can tolerate 100 newtons downstream of that? So I would probably try and slow this roller down so I could lower T8 a little bit. Or, if necessary, speed up the next driven roller so I could raise T9 a little bit, or maybe both. But you've got 4 variables, you've got to decide how to fix them and what's appropriate for your case. Summary of the capstan formula. For driven rollers, friction drive rollers, you definitely don't want to slip on those. You spent a lot of money for that drive to control the velocity of the web. If it's your master roller, it's controlling the stability of your whole process, and so you'd like to never slip on that under any typical condition that you'd expect to see. For idlers, you'd like to certainly not slip when you're running at steady state, and ideally you wouldn't slip on startup and shutdown. But if it's not a fatal web break situation, you might tolerate a little bit of slipping on occasion. And then if you do have sliding contact by way of bow bars, D-bars, and things like that, the capstan formula is used as an equality. TH over TL equals E to the mu theta in a slipping situation. Now, I have one slide here that is always brought up as a question about contact pressure between a web and the surface of a roller. Basically, the pressure that the web applies to the roller is equal to the tension force in the web divided by the width of the web divided by the radius of the roller. And so you can calculate what that pressure is. Now, obviously, then higher tension gives you more pressure. For a given amount of tension, a smaller radius roller or a narrower web gives you more pressure. In the previous section, we covered the capstan formula, when a web will slip on a roller, the tension ratio across the sliding surface, and how to measure the coefficient of friction between a web and a roller. In this section, we're going to look deeper into the traction of webs on rollers. We're going to talk about air entrainment, the coefficient of traction, COT or mu-T, web and roller properties that affect traction, the consequences of loss of traction, and methods to enhance traction. Now, air entrainment work that I'm going to talk about was done by Keith Ducote at Oklahoma State University back in the 90s. And basically what his work involved and found is there's a thin layer of air that's carried along by the webs and roller surfaces and becomes trapped between the web and the roller. The faster you go, the more and thicker the trapped air film. Now, eventually this air film will separate the web from the roller. The surface roughness of the web and the roller keeps them in partial contact, but when the initial air film thickness reaches a certain value, traction starts to decrease. And when the exiting air film thickness reaches a certain value, all contact between the web and the roller is lost. Now, side leakage out the sides of the web and web porosity decrease the film thickness as the web traverses the roller. This picture shows roughly how a web traverses a roller. As it approaches the roller, both the web and the roller surface are bringing air into the interface. There's an initial transition zone where the web is not yet contacting the surface of the roller and has no traction. The faster you go, the farther this transition zone reaches into the roller. The slower you go, the shorter it is. After that, there is what's considered the constant air pressure zone, where the web is applying pressure against the air underneath it, either causing it to flow through pores in the web or leak out the sides. And in the previous presentation, we talked about the constant air the pressure that the web exerts against the surface of the roller. That's what's happening here. Towards the exit of the roller is what's called the micro creep zone. And this is where the web is adjusting from its incoming tension to its outgoing tension. The angle that's involved here is actually the theta that would be calculated by the capstan formula for the tension ratio and the coefficient of friction involved. So in the micro creep zone, the web is adjusting itself from one tension to another, which means it is increasing in length or contracting a little bit as it goes from high to low or low to high tension. So there is some movement of the web against the surface of the roll at this location. That's why it's called micro creep. To avoid slip, the contact angle must be greater than the theta that's calculated for the micro creep zone, and the transition zone must not extend all the way around the roller to the micro creep zone. Now, the air film thickness can be calculated from what's called the Knox-Sweeney equation. There are several names for it. It's the same formula basically that's applied to oil films and bearings and things like that. So we have an initial film thickness H sub 0 that's equal to K, which is an entry constant. The radius of the roller, that's times a quantity 6n, where n is the dynamic viscosity of air, but you could use any other fluid in here, so it could be water, oil, whatever. The sums of the velocity of the web and the roller. They're both in here because you might have a case where the web is moving and a surface is not. A roller is standing still or it's sliding contact over a non-rotating bar. This is all divided by the material stress, the pounds per inch, newtons per meter of the web coming in. And that quantity in brackets is to the 2/3 power. So it must be, in the end, it must be dimensionless. And so you can calculate that air film thickness. Looks like an ugly formula, but it works really well in Excel. Keith put this together. So we've got the thickness of the air film at any point along the roller is equal to the initial air film thickness minus a term that describes how much web leaks out through the porosity, or how much air leaks out through the porosity of the web, where air is the web permeability. And again, we have the stress term and the velocity terms in the denominator. And then also a term that describes the amount of air leaking out the sides of the web. And so you can find the air film thickness that resides in any part of the contact zone. Now, air leakage out the side, again, a formula that was developed by Keith. It looks ugly again, but you plug it into Excel, it works fine. By putting all these together, you can calculate air film thickness as a function of speed and at any point in the roller. Now we have here a calculation that shows for a 1 meter wide solid film, so no porosity, at 40 newtons of tension on a 0.2 meter diameter roller, the air film thickness as a function of speed. And so as we get up to a roller speed of 10 meters per second, we've developed an air film thickness of about a tenth of a millimeter, or about 4/1000ths of an inch. Again, not a huge thickness, but certainly compared to the roughness of some webs and rollers, quite thick. So before we can talk about if a web slides or not, what we have to understand is the roughness of the webs in the roller act like tread, and they allow this air to give it some place to go and allow it to flow out from between the web and the roller. So they make the contacts between the web and the surface of the roller. Now, there's a couple of different ways to measure roughness. And the first one we're going to talk about is the RA value, or the average roughness of the surfaces. Now, roughness can be measured on a rigid surface like a roller with a device called a profilometer. For us old-timers, it looks like a phonograph needle sliding across the surface, but it generates a signal as it tracks the surface. This is digitally manipulated, and a value called the roughness average is calculated from that, and it's the average distance of the peaks and the valleys from the mean height. And so that's the RA value. Now, webs have a roughness and rollers have a roughness, and so we add those two together and divide by 2, and we get the RA average. And so that's one of the roughnesses that we have to keep track of. The second roughness measurement that we have to think about is the RQ value. It used to be called the RMS roughness. But what this does is this is a measure of the average of the squares of the distances of the peaks and the valleys above and below the mean. And so in doing this, it is looking at the square value, so it exaggerates the peakiness of the web. It focuses and emphasizes the peakiness, the really high points on the web that might be the last thing to be in contact between the web and the roller. And so the RQ composite value is found by taking the square root of the squares of the RQ value for the roller and the RQ value for the web. We end up with an RQ composite number that looks at both of those surfaces. Now, if we put these all together, that we've talked about the air film thickness, the two references, what we find is this. When the air film thickness is less than the RA average value, you have complete the static coefficient of friction or the slow speed coefficient of friction that we measured with our test. Now, as you run faster and the air film thickness increases until you get to the 3RQ value, at this point you have completely separated the web from the roller. All the peaks are separated, and our coefficient of friction at this point, are now called coefficient of traction, is 0. There is no contact between the web and the roller. And what Keith did is, in between these 2 points, he basically just put a straight line between them. And so you come up with a fairly easy to understand graph of when the air film thickness is less than the RA value, you've got complete traction. When it exceeds the 3RQ value, you have no traction. And in between those two, it was pretty well approximated by a straight line relationship. And that, again, is easy enough to model. When you do have complete separation, there is still a force between the web and a roller due to the shear of the air. It's normally a very small force, and typically it can be ignored. But again, it can be calculated. If you have other liquids, oils, waters, it may have a more significant value, but normally for air, it is a pretty small value. I have a graphic here that shows how the web separates from the roller under the different conditions of air film relative to the roughness. The factors that affect the coefficient of traction come out of the formula. Velocity is the first one here. Higher velocity decreases the coefficient of traction. So the faster you run, the less traction you're going to have if air entrainment is a factor. Now that typically is going to mean that in the future this problem is only going to get worse because everybody wants to run faster. And slowing down generally is not an option. Tension, higher tension increases the coefficient of traction. It applies more pressure between the web and the roller, squeezes the air out, compresses it more, makes more contact. But typically, as we want to run thinner and thinner films at lower and lower tensions, this is not going to be a solution that we can normally apply. And it does suggest that things may only get worse in the future. Roughness of the webs and the roller surfaces, you may not have an option to change the web, but in some cases you can go for a rougher roller surface. If your web can tolerate the roughness, there are all of the spray coatings, the metallized sprays, and various things that you can do to the roller to increase the roughness. The radius of the roller, the larger the radius, that decreases the traction. You go back to the pressure formula, and the bigger the radius, the less the pressure of the web against the surface of the roller. And so the coefficient of friction is decreased, typically, coefficient of traction. Again, if you have a small roller pilot line that runs well and you design a larger diameter roller, for wider webs in a production line, you may find that what worked well on the small rollers has some traction problems on larger rollers. Now, porosity of the web, obviously if the air can escape through the web, that will increase the coefficient of traction, but typically that's not something you can adjust. You have a web, you want to run that web. Wrap angle. Increasing the wrap angle gives the air more time to escape, and so that does increase the coefficient of traction. That may be something you can do. Certainly if you have a friction drive S-wraps, you can increase the angle maybe up to 540 degrees. If you have single driven rollers, typically it's harder to do much more than 180 degrees. Maybe a little bit more if you position an idler to increase the wrap angle. And width of the web, the wider the web, the less side leakage there is, and so generally the lower the coefficient of traction. In fact, you sometimes see in wide webs, you see roller wear on the edges of the web. That's where the air is leaked out and the web has touched the surface. That may be the only part of your web that's in traction with the roller. There are some problems that you'll see from loss of traction. Tension instability being the first one we notice typically. Tension relies on velocity control, and if you're sliding or losing traction, you're not in control of your velocity. And so you're not in control of your tension. What may be worse is intermittent traction, and so your tensions are going up, going down, going up, going down, depending on if you're in traction or not and what conditions might be influencing that. Phase and registration instability are a sign that you might not be in traction. Again, they rely on good velocity control. And so loss of traction can cause various print phasing, product phasing to go in and out on seemingly a random basis sometimes. If your line is not responding to the controls, it could be that you are not in traction with the rollers that control phase and registration. Tracking instability. Webs are guided by the rollers only when they're in traction with the rollers. Again, we follow the right angle rule where the web approaches the axis of the roller at right angles when it's in traction. If it's sliding on a roller, it's free to go wherever the forces of nature push it. And so it can go to the left, it can go to the right, it can do whatever. It's just like your car when you get on ice. It goes where the forces of nature guide it, which is usually downhill. And so you need traction to maintain your tracking stability. Web scratching. If you have relative motion between your webs and your rollers, it's possible to scratch the web. And depending on your product, this could be a serious defect. If you have a nice glossy plastic film, you don't want to be sliding on a roller. Dust generation. I came out of a nonwovens in a tissue paper environment. Sliding makes lots of dust, and so you didn't want to slide because of the dust problems that you could create. And so you can create a lot of problems from loss of traction, and they're not always obvious to you. Lines can run if you're not in traction with a driven roller. It may run just fine, except it's not doing what you think it is. So they're not always obvious that you've lost traction. Now, there are some things that improve from a loss of traction, but these are not recommended solutions. One is your web is less likely to wrinkle if it's sliding on a roll surface. It takes compressive forces in the web to make wrinkles, and if you don't have much traction, you may not be able to develop those compressive forces. In fact, if you have a web that has a lot of waviness in it and it's going over a sliding surface, that will typically cause it to flatten out. We do have examples of that in bow bars and D-bars, and the operators invariably find that if you stop a roller from turning, it may solve a wrinkle problem. So certainly not a recommended solution, but the lower the traction, the less likely your webs are to wrinkle. Also, less tension lost idlers means more tension available to the web. So if you have a couple of bad idlers in a web path, stiff bearings, don't want to turn well, and you're sliding on them, that simply means that your web is not having to give all of the tension that those idlers are demanding, and so more of it is left in the web. If somehow you force the web into traction with those rollers, they could eat up a lot of available tension and leave you with low tension upstream of those bad idlers. How would you know if you're in sliding over a roller? Well, in a lot of cases, it's as easy as measuring the speed of idlers. So if you have a driven roll and you measure the rotational speed of it and calculate the surface speed of it, it should be running within 1 or 2% of the speed of the next downstream driven roller. If it's not, something is sliding. Either the idler that you're measuring or the web is not being pulled at the appropriate speed by the roller that's doing the pulling. So you might measure 2 or 3 idlers in that path and see if they're all 1 or 2% or if some of them are at 80% of the expected web speed. So you might be able to find it that way. Definitely erratic tracking behavior. I've seen webs that run fine through the first several spans and then become very erratic, which tells me that they're going in and out of traction once they get to that point in the web path. Maybe a bad roller, it may be that it doesn't have enough wrap angle built into it, or a worn surface. or just very low tension in that area. But erratic tracking, especially that happens after you've seen the web behave nicely in the first several spans. Lack of response to velocity or phase and registration controls. I've seen cases where you speed up a roller and nothing happens to tension. And that's telling you that something is probably slipping. Same thing with phase and registration controls. You make an adjustment, you don't see the expected result, and it's probably because you're slipping. Now, there are some solutions here, and again, these fall out of the formulas that we've looked at. More wrap angle helps. And so if that's easy to do and inexpensive, that might be a solution. More tension could help improve traction. That's not always a desirable option, especially if you're trying to run low modulus, thin, low tension webs. Tread is a common solution. This might be by way of rough texture. Some of the metal sprays create nice rough textures that can penetrate the air films and provide traction. Other types of coatings might do that. You can buy tapes that provide, again, rough textures for the web that can help you penetrate the air film and give you improve your traction. Another common solution is grooves in the idler. These might be machined axially across the width of the roller, circumferentially, or in some spiral pattern. Designing grooves is a whole science in itself. Probably don't want nice, sharp, peaky grooves because they can scratch your web. It's nice to have some flat lands on top so that you don't do any scratching. You can have nice rectangular grooves. That works fine. I've seen rollers with spirals cut in them. Now you gotta recognize that these spirals are not cut as a way of removing wrinkles. They're in here, especially in rigid metal rollers, they're in here for the purpose of allowing the air to escape, giving the air someplace to go to help maintain traction. But they can be cut on spirals of various patterns. There's a variety of ways that manufacturers can cut the rolls, but the objective is to give the air someplace to go. As far as the grooves themselves, narrow grooves so that you don't pull the web down in the hole into the valley. Typically, you want the depth to be a little bit greater than the width. Fine pitch is good for that. I've seen rollers where as you run your finger across them, it's like running your finger across a phonograph. They're very fine pitch grooves machined into them. And whether they're spiral or circumferential or axial is just a machining question. And so they all do the same thing, get rid of the air. Some variations on the Capstan formula here. The basic formula, TH over TL equals E to the mu theta. You can modify the formula a little bit for a vacuum roll. What you'll see in this formula is that it does allow TL to be 0. Basis weight of the web, whereas vacuum is holding the web on the surface of the roller, basis weight is throwing the web off the surface of the roller, and so it actually decreases traction. So if you have very heavy webs running at very high speeds, it's possible to sling the web off the surface of the roller. Any questions on any of this? You can feel free to contact me at ronjlynch@hotmail.com or my phone number. Happy to answer questions. Hopefully I'm here in person presenting, but if not, feel free to contact me. I thank you.